A team just cracked open the one problem that's been blocking quantum computers from scaling to millions of qubits, and they did it by reading information that was designed to be unreadable.
We're talking about Majorana qubits, the holy grail of quantum computing. On February 11th, 2026, researchers at QTech, which is Delft University of Technology in the Netherlands, published a paper in Nature showing they've achieved the first single-shot, real-time readout of quantum information stored in Majorana modes. And to understand why that's massive, we need to talk about what makes these qubits so special.
Okay, so back up for me. What even is a Majorana particle?
So in 1937, an Italian physicist named Ettore Majorana predicted a particle that is its own antiparticle. When matter meets antimatter, they annihilate each other, right? But Majorana said there should be particles where the matter and antimatter versions are the same thing. For decades, nobody could find them in nature. But in the 2010s, physicists realized you could engineer something that behaves like a Majorana particle inside certain materials, specifically at the boundary of superconductors and semiconductors.
And these engineered Majorana particles are useful for quantum computing
Because of how they store information. Normal qubits, think Google's superconducting qubits or IBMs, they store quantum information locally in one spot. It's like writing your password on a sticky note. Any noise, any vibration, any stray electromagnetic field can mess it up. That's called decoherence, and it's the single biggest problem in quantum computing right now. Majorana qubits do something fundamentally different. They split the quantum information across 2 points in space. The data isn't stored in either location, it's stored in the relationship between them. It's like tearing a secret message in half and putting each half in a separate safe. No one can read it by opening just one safe.
so noise hitting one location can't destroy the information because the information isn't fully there?
Right? That's called topological protection. The information is encoded in the topology, the global shape of the quantum state, rather than local properties. Microsoft has been betting their entire quantum strategy on this for over 20 years.
20 years is a long bet. So what was the missing piece?
Reading the qubit, here's the irony. The same property that makes Majorana qubits so stable also makes them incredibly hard to measure, because the information is non-local, a standard local sensor literally cannot see it. The QTech team, led by researchers including Francesco Zatelli, solved this using something called quantum capacitance measurement. Instead of trying to detect charge at one point, they connected an RF resonator to the superconductor, linking the two Majorana modes and measured how the entire system responds.
So they're measuring the whole chain at once instead of poking at individual spots?
That's it. They built what's called a minimal Kitaev chain, two semiconductor quantum dots coupled through a superconductor. When they tried conventional charge sensing, the local sensors saw nothing, completely blind, but the quantum capacitance probe could clearly distinguish between the even and odd parity states. That's the 0 and 1 of the qubit.
How stable was it?
They measured parity coherence times exceeding 1 millisecond. Now that might sound tiny, but in the quantum world, that's an eternity. Most superconducting qubits need error correction within microseconds. A millisecond gives you 1,000 times more room to work with.
So this is what Microsoft was waiting for with their Majorana 1 chip announcement last year.
It validates the entire approach. Microsoft announced the Majorana 1 processor in 2025, but critics pointed out they hadn't demonstrated actual readout of the topological states. This Nature paper, from an independent academic team using a different fabrication approach, fills that gap. The QKit project, funded by the European Innovation Council, built the chain from the bottom up, adding quantum dots one by one. It's modular, scalable, and now proven readable.
Okay, so we might actually get quantum computers that don't need a million error correction qubits for every useful qubit?
That's the dream. Current quantum computers need somewhere between 1,000 to 10,000 physical qubits per logical qubit because of errors. Topological qubits could dramatically reduce that ratio, which is how you get from today's few hundred qubit machines to the million qubit systems needed for real breakthroughs.
Now, you mentioned there's a second piece of this puzzle, something about a quantum internet.
Yes. And the timing is wild. The same week, a team led by Pan Jianwei at the University of Science and Technology of China published in Science showing device-independent quantum key distribution over 100 kilometers of optical fiber using single rubidium atoms.
Device independent, that's the key phrase there, right?
Huge. Regular quantum key distribution, QKD, lets two people share an encryption key where any eavesdropping attempt is detectable because it disturbs the quantum state. But here's the catch. Regular QKD assumes your devices are working perfectly. If there's a hardware flaw, or worse, if someone tampered with the equipment, the security guarantees collapse.
So you're trusting the hardware manufacturer not to have built in a backdoor.
Right. Device-independent QKD removes that trust entirely. The security comes purely from the laws of quantum physics, specifically from violating what's called a Bell inequality. If the measurement results violate the Bell inequality, the laws of physics mathematically guarantee the key is secure. It doesn't matter if the devices were built by your adversary.
And previous attempts at this only worked over a few hundred meters.
The record before this was laboratory scale. Think across a room. The problem is that quantum signals degrade exponentially over fiber. Pan's team made two critical innovations. First, they used single photon interference for entanglement heralding, which boosted the entangling rate by orders of magnitude. Second, quantum frequency conversion shifted the photons to telecom wavelengths where fiber loss is lowest.
How did they actually generate the keys?
They trapped individual rubidium atoms in laser beams at two separate nodes, created quantum entanglement between them through single photons sent through the fiber. Then they measured the atom states at each end and compared results to generate matching strings of zeros and ones, the shared secret key.
And they maintained Bell inequality violations the whole distance?
At every distance tested 11, 20, 50, 70, and 100 kilometers, the secure key rate drops with distance because of fiber loss, but it stayed positive all the way to 100 kilometers. That's city scale. You could connect government buildings, banks, data centers.
So let me connect these two stories. We've got Majorana qubits that could give us stable, scalable quantum computers and device-independent quantum encryption that could protect against those same quantum computers breaking current encryption. It's like we're building the weapon and the shield at the same time.
That's a perfect way to frame it. Right now, most internet encryption relies on math problems that quantum computers could theoretically solve, RSA, elliptic curve cryptography. The threat is called harvest now, decrypt later. Adversaries are already storing encrypted data today, waiting for quantum computers powerful enough to crack it.
And DIQKD would be immune to that because the security isn't based on math problems.
It's based on the fundamental structure of reality. No computer, quantum or classical, can break the laws of physics. But here's what makes these two breakthroughs converge. The rubidium atom nodes in the QKD experiment are essentially quantum memory nodes. Scale those up, and you don't just have encryption, you have the backbone of a quantum internet where quantum computers can talk to each other.
When does this actually reach people?
The Majorana readout is still a lab result, maybe 5 to 10 years from commercial quantum processors using topological qubits. The QKD experiment had all nodes in the same lab, so the locality loophole isn't fully closed yet, but the trajectory is clear. Microsoft, Google, and national programs in China, the EU, and the US are all racing. The pieces are falling into place faster than most people expected.
The missing piece just got found, and now the puzzle is starting to look like a picture.